Oh, that's loud. Okay. All right. Good morning, class. This is lesson 5. Lesson 5 covering section 1.7 of our textbook. Hopefully, the video shouldn't be all pixelated the way it was towards the end of yesterday's video. I'm not sure why it was doing that, but it should be fine today. So we're covering lesson 5, section 1.7. Remember that homework 1 is due tonight by midnight. We're also going to have, of course, there's participation day 5 we'll cover today during the video. So make sure you get those homeworks turned in. If you're needing more time, it is fine if you need to turn it in tomorrow. However, remember that there is going to be a late penalty for that. Each day late, it will drop by 10%. Once it's more than 3 days, so if it's 4 or more days late, there's a 50% penalty. But at that point, it's not going to drop any further, right? So if at the end of the semester you have some missing homework you haven't done, you can still do them for at least a 50, which, okay, maybe that's not great. But that's still going to be a heck of a lot better than a 0. So if you're missing assignments towards the end of the semester, just keep that in mind. That can be a way that has, in the past, sometimes has helped students get those few points they needed for the next letter grade. Right, okay. Let's go ahead and look at today's lecture plan then. This is section 1.7. So we've seen so far that there's some, what is a homogeneous system? This is AX equal to 0. Remember, multiplication, matrix multiplication, is the same thing as linear combinations, right? So if the matrix A has, let's say, 3 columns, so these are column vectors, then X has to have a scalar that is applied to each column, and this multiplication is defined to be a linear combination. And in the homogeneous case, this is set equal to 0. This is the homogeneous linear system. Right, so nothing new here. I just want to refresh this because this is going to be super important and relevant for today's lecture. So we had 2 cases that could happen here when we're taking this linear combination of the columns. Either case 1, there is only the trivial solution. And recall, when does this happen? This is when there are no free variables. Or to put another way, having no free variables is the same thing. So I'm doing this double arrow with the arrow going in both directions. This is an if and only if. No free variables means you have a pivot in every column. Right, so this is the special case. Still always have the trivial solution, but non-trivial solutions also exist. Which non-trivial solutions do not always exist. If there are no free variables, there are no non-trivial solutions. So non-trivial solutions exist only when free variables are present. Right? So we know this. We've seen this from yesterday's lecture. Okay, why am I bringing this up again? Why am I writing all of this again? Well, we're actually going to have a very special definition, a very special property we're going to consider when we're taking linear combinations and we have only the trivial solution. We have a special name for this. So definition And I apologize, my marker seems to be dying. I'm going to have to get some new markers today. So here's our definition. Given a set of vectors, so I'm using curly brackets since that's set notation. This is a set of vectors, v1, v2, ... vp. So I have a p number of vectors in Rn. Again, what does that mean? That means each vector is a column vector with n entries, where each entry is a real number. Okay, we're going to say the set of vectors is linearly independent. Linearly independent. This is going to be a super important vocabulary. We're going to say a set of vectors is linearly independent if the homogeneous linear combination of the set of the vectors, so of the vectors, so what is that linear combination? Well, I can multiply v1 by a scalar, plus I can multiply v2 by a scalar, plus ... I can multiply vp by a scalar. But this is the homogeneous combination, so it's set equal to 0. We're going to say these vectors are linearly independent if the homogeneous linear combination of the vectors has only the trivial solution. Right? Again, what does that mean? How do we know if we have only the trivial solution? That means there are no free variables. When I put my column vectors together, there are no free variables. I have a pivot in every column, right? This is what it means to be linearly independent. So then otherwise, if we have the case where, oh, there is a free variable, then we're going to say it is linearly dependent. So otherwise, if this does not happen, then the vectors or rather the set of vectors, is called dependent. So anytime we're dealing with any matrix of column vectors, we can now ask the question, okay, are these column vectors linearly independent? Are these column vectors linearly dependent? And the whole question there is just trying to answer, do you have free variables or not, right? That's going to answer your question. Do you have a pivot in every column? But why do we use this phrasing linearly independent, linearly dependent? Why are these words helpful here? What does this mean geometrically? Well, let's take a look in R2 where it's easy to graph this. So we have kind of this recurring example. Think again back to these two vectors that I've mentioned a couple of times. Let's say A is this matrix 1, 0, 0, 1. So column 1 is the vector in the x-axis direction, right? Column 2 is the vector in the y-axis direction. Now imagine you're trying to take a linear combination of these vectors and you want to add them together to result in 0. Well, okay, we already know by looking at the matrix, I have a pivot in every column. That's going to tell us we have only the trivial solution. Why? Is there any way I can add these vectors together to get 0 without multiplying by 0? Well, if I multiply this first vector 1, 0 by something that was not entry in the second column to somehow, but because I have a 0 here in the second column, it's not going to be possible for them to cancel each other out, right? Which means the only way for these two vectors to add together to give me 0 is if I multiply each one by 0. Has only the trivial solution. So these vectors are then called, so therefore, I'll use this notation with the dot, with the triangle dots. If you've taken discrete math, you've seen this notation before. This is just proof notation to say therefore, thus, or this implies. That's what this symbol means. So these dots in a triangle symbol, this just says we have only the trivial solution. Therefore, the vectors are linearly independent. Therefore, linearly independent. But look at the picture. What does it mean to be linearly independent? Well, in the case of R2, I'm saying these vectors are linearly independent if they quite literally exist on different lines. The lines these vectors are on are independent of one another. Okay, what's a dependent example? A dependent example would mean I have a free variable. So consider something like this, right? Now I only have the one pivot. I have a free variable in the second column. But when I look at the picture here, well, here's my vector 1, 0. And then here's my vector 2, 0. Are these now dependent? Well, or does this have a non-trivial solution? Well, yeah, I mean, you can pretty quickly see if I take 2 times 2, 0, I can get the 0 vector, right? So a non-trivial solution exists. A non-trivial solution exists. Therefore, linearly dependent, right? But again, visually, what does this mean? The lines that these vectors exist on are not independent of one another. The vector 1, 0 and the vector 2, 0 are both vectors on the x-axis line. They're not dependent of each other. In fact, this second vector is just a multiple of the first. They are not linearly independent because they're on the same line. Therefore, we call them linearly dependent. So this is a visual representation of what we mean by linearly independent. The vectors are on different lines, or linearly dependent. The vectors are some combination of each other, right? Another way to see this is you could say, oh, well, this is, after all, just an equation. I can add, right? I can add things over just like I can with regular algebra. What we have here is 1 times 2, 0 is equal to 2 times 1, 0. In other words, when you have linear dependence, that means one of your vectors, such as 2, 0, is really just a combination of the other vectors you have. In other words, your free variable vectors, your vectors that have a free variable, those vectors are going to be a combination of your pivot vectors. So this is the key point I want to highlight here. Okay, I'm going to leave it on the board for the moment before we continue. And let's see, I have this lecture. So I'm going to erase our examples. Okay. So let's see. Have we covered the high points I want to hit with the definitions? Right. So we know having only the trivial solution, we have this direct connection with are there free variables or not. To be linearly independent means we have only the trivial solution, meaning no free variables. Otherwise, if we have free variables, we're going to call it linearly dependent. Okay, good. So we can see other examples. And we can say, okay, well, what about if I have the vectors, let's say 1, 1, 2, 2, and 0, 0, right? You could have a question like this where you're given 3 vectors, and the question could say, are these vectors linearly independent or are they linearly dependent? Well, as you might guess from what we just did, we know we have linearly dependence if 2 vectors are on the same line, or in other words, 2 vectors are just multiples of each other. Well, we can see right away that V2 equals 2 times V1. V2 is a combination of V1, meaning V2 is dependent on V1, right? I can create V10 of one another because they're on the not linearly independent. This is linearly dependent. These are linearly dependent. But note, I could come to this answer. I could figure this out just by looking at them. I didn't have to do anything else here. I didn't have to create a matrix and row reduce. I didn't have to do any other steps here. Just by noticing that one vector is a multiple of the other, I can automatically stop and say, oh, if one is a multiple, it must be actually that that vector is on the same line. Therefore, they're linearly dependent. But there's also a quicker way we can see a solution here. One of the vectors here is the 0 vector. And one issue with the 0 vector is that for any vector, so for any vector, I can take 0 times vector. 0 is always a scalar I can use, right? But I can also take 0 times V2, right? In other words, anytime you're looking at a set of vectors, if the 0 vector is one of them, it is automatically a multiple of the other vectors. Why? Because any other vector, multiply it by 0, and you get the 0 vector. So anytime you see the 0 vector, it is automatically dependent. So that's a key thing here. This is always going to happen. If a set of vectors has the 0 vector, then the set is dependent, okay? Now, why is that happening? Remember, linearly independent or linearly dependent, another way to think of this is about recognizing, do we have a pivot in every column, or do I have a free variable? But if you have a column of all zeros, then when you row reduce the matrix, those zeros aren't going to go away, right? If you have a column of all zeros, then when you row reduce, nothing's going to change those zeros in the columns. And so this is going to have a free variable for that column, right? And if you have a free variable, automatically, whenever you have a column of zeros, that means you're also automatically linearly dependent. But okay, let's suppose maybe you don't notice right off the bat that we have multiples here. How else could you solve this? You could put them in a matrix and row reduce, and you just want to check, hey, do I have a pivot in every column or not? So I also want to highlight here that when we're creating this matrix, this is a matrix of column vectors, right? there's no equal sign going on here, which means when I have this column of zeros, this is not an equals column, right? This is a key point. If you have a column with zeros in them, it is not necessarily the equals column unless the problem specifically has you equal to 0, right? In this case, we don't know anything about setting the equal to anything. This is not the equals column. Not equals column. So this is not an augmented matrix. Okay, so we can't say anything about whether the system is consistent or inconsistent. Those are terms which only apply to augmented matrices. Okay, good. But now we're trying to see, okay, where are my pivots? I need to reduce the matrix. I'd like to get a pivot here. So I'm going to modify row 2. By taking row 2, I'm going to subtract row 1 from it. And this is going to give me this new matrix, 0, 0, 0. So we're all done. I have this row of zeros, so I can't get a pivot in the second row, so I'm done. Therefore, linearly dependent. So there's two different ways to solve this kind of problem here. I also want to highlight here, there may be some homework problems that are talking about like the dimension of spaces. Recall that when we were talking about spans, the number of pivots for your vectors in a span determines the dimension of the span, right? If I take the span of 1, 0, well, this space is, so this is a side tangent that might relate to the homework. This space is one-dimensional. Why? This vector is in R2. Why am I calling this space one-dimensional? Well, I'm calling it one-dimensional because remember, span is the set of all possible linear combinations. So let me erase what I have here. We're going to go off on a little side tangent here about span. If I think about, if I'm taking the span of only the vector 1, 0, my marker's dying. I do have this red marker. I'm hoping it'll show up on the screen okay. Yeah, that's barely visible. Let's see, how about this? Oh yeah, that's good. All right. I guess, fair warning, if there are any students who are possibly red-green colorblind, I apologize for what I'm about to do. Please let me know if you are, and then I'll know red markers are not good. Yeah, okay. Let's try to make the most of this. All right. So if I'm taking a span, which is only linear combinations of this, because I can only move in one direction, one possible direction, right? I can take multiples, I can take combinations of only one vector, right? This span is the set of all possible linear combinations of that vector. And there's only one vector here, such that x1 is in R. It's a real number, right? This is what the span is, the set of all possible combinations, right? Well, I could double it. So I could go over here. I could triple it. I could go further down here. I can go anywhere in this positive direction. I can also go in the negative direction, or more in the negative direction, so on and so forth. I can travel anywhere on this x-axis, right? In other words, I can travel anywhere on this line. But in terms of like, okay, well, how many degrees of freedom do I have? What is a degree of freedom? This is just referring to how many different directions can I move in, right? I can't move everywhere in R2, right? In order to move everywhere in R2, I would need one more independent direction, such as the y-axis. But because I only have this one direction, I can either go back or forth on this one direction. This space is one-dimensional. Right? So again, I want to highlight the number of pivots in your span is going to tell you the dimension of that space, right? So if I take the span of one, 0, 1, allows me to reach everything in R2. How can I tell? Because I have two pivots. I have two independent directions I can move in. But I also want to highlight the number of vectors in your span is not necessarily the dimension, right? If I take the span of 1, 0, and 2, 0, well, 2, 0 is just a multiple of 1, 0, right? This isn't a new direction I can move in. It's on the same line, right? So taking combination of these two guys, even though there are two vectors, I still only have one pivot, right? And so this is one-dimensional. And this is despite what space these vectors actually live in, right? In other words, the dimension of a space is determined by how many directions can you move in, right? But if I'm defining a span to be I can only move in this one direction, we're going to call it one-dimensional. If you have two independent directions, in other words, the dimension of a space is how many independent directions can you move in. R2 only has at most 2, right? Okay, good. So we had that little side tangent. Let me erase that then. Okay. Goodness, yeah, that black is not very good in the video. I'll get some new markers. I'll stop using that black marker. For now, I'll have a new black marker for tomorrow. Okay, good. So I want to do another example where it's not so obvious just by looking at it. Here, we're given some matrix with column vectors. And here, our matrix is 0, 1, 5, 1, 2, 8, 4, -1, 0. And the question is, are these column vectors linearly independent or dependent? Right? That's the question we're trying to answer here. Well, just by looking at it, like, okay, just at a first glance, none of these vectors necessarily seem to be multiples of each other, right? The second vector is not a multiple of the first. The third is not a multiple of the first. But it's possible. What if one of these vectors is actually a combination of the others? What if there's some way for me to add the first two vectors together that would give me the third? How would I tell? Well, in this kind of case where you can't tell just by looking at the columns if they're independent or not, we really do have to row reduce the matrix and check, do I have a pivot in every column, right? So that's what we're going to do here. But first, in order to get a pivot in the first row, I already have a 0 there. I want that. I want to have a pivot there if I can. I'm going to swap row 1 and row 2, which is fine. Remember, each row you can think of as it just being the equation. I'm just swapping the order I'm looking at the equations in. That's not going to change anything here, right? So I have 1, 2, -1, 0, 1, 4, 5, 8, 0, right? And now I can start with the row reduction. So I'm going to take, I already have a 0 here, so I need to modify row 3. I'm going to take row 3 and subtract 5 times row 1. So we have 1, 2, negative 1, 0, 1, 4, 0. 2 times negative 5 is negative 10. When I add negative 2, negative 1 times negative 5 is a positive 5. So when I add, we get 5. Okay, looks fine so far. I like to get a pivot here, so I need to get zeros below it. So I'm going to take row 3. I'm going to use row 3 to modify because I'm going to use the row with a pivot where I'm trying to get zeros. So I'm going to add 2 times row 2. And we have 1, 2, negative 1, 0, 1, 4, 0. 1 times 2 is 2 when we add 0. 4 times 2 is 8 when we add 13. Well, lo and behold, what happened? I have a pivot in every column. I have zeros all below them. They're the leading zero of each row, or they're the leading non-zero entry of each row. And nearly independent. So this is being able to tell when you have linearly independence or dependence is going to be crucial as we go in the class. We're going to find out that this property also tells us other things. This property is also going to be super important when we start talking about other properties, other things we can do with matrix equations, so on and so forth. So this is an essential building block. Now you may also realize that as we continue, like, all right, we seem to be adding a bunch of new vocabulary words. And in fact, that's probably just the nature of linear algebra. Linear algebra does have a lot of vocabulary. So this first chapter we're going through, you're going to see we're going to add new terms that mean this or that, blah, 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 blah. It can be a lot. It can be overwhelming. But understanding these different definitions is going to be crucial as we continue in the course this summer. Okay. Let's see. Are there other things I want to highlight here? Right. Great. Okay. Let's go ahead and look at today's participation question then. So let me switch over to sharing my screen. Sharing screen. Here we go. All right. We are now looking at participation day 5. Participation day 5, determine if the following set of vectors is linearly independent or linearly dependent. So recall, one way of doing this is just to say, you know, are these two vectors multiples of each other? If they're multiples, that means they're on the same line, therefore they are dependent. If they are not multiples, I only have 2. So, okay, what happens here? Well, so I'm just going to imagine, you know, what would I have to multiply the first vector by to get the second vector? Well, to turn negative 2 into 3, I would have to take negative 2. So I'm writing this on the board in the background, but you can write on paper or something else as I'm saying this. I want to think about, well, negative 2, I would have to multiply by a negative 3/2. That would equal 3, right? Negative 2 times a negative 3/2 is a positive 3. Okay. So if these vectors are multiple, that means that scalar, negative 3/2, should work for each entry. Okay, well, 4 times negative 3/2 is going to be negative 6, right? Because 4 divided by 2 is 2. 2 times negative 3 is negative 6. Okay. 6 times negative 3/2. 6 divided by 2 is 3. 3 times negative 3 is negative 9. Okay, looks good so far. And then lastly, 10 times negative 3/2. Well, 10 divided by 2 is 5 times negative 3 is negative 15. In other words, what's happening here? For each entry, in order to get the second vector to be a multiple of the first, I'm having to flip the sign, right? Negative 2, this became positive. 4 became negative, 6 became negative. But 10 does not flip signs. I have a positive 15 here. This tells us that the second column vector is not a multiple of the first vector. I'll turn off the screen share again so you can see what I'm talking about here. In order for these two vectors to be multiples of each other, right? You can imagine taking this column, I can multiply it by something to get the other column vector, right? This scalar works for all three entries except for the final entry, right? So when we come back to this problem here, these are then not multiples of each other. Because they're not multiples, that means they're on different lines. If you like, you can also put these two column vectors into a column and row reduce them, and you'll see, yeah, in fact, you'll get a pivot in each column. So these vectors are linearly independent. So for today's question, participation day 5, just start assignment, type in linearly independent, and that's it. That's all I'm looking for. Go ahead and submit assignment, and you're done for today's participation question. A few other things I want to highlight. Notice here, there is the option for a new attempt, right? So for any of these participation questions, if like you attempt it first on your own or something, and you realize you've done something wrong and you want to go back and resubmit, that's fine. Go back and resubmit. When I get to grading the participation questions, I'm going to grade whichever participation question was submitted last, right? So if you have first submission, a second submission, a third submission, I'm going to grade that third submission, right? Now, with that being said, that does not mean that you're going to get multiple attempts at these once I grade them, right? If you submit it once and it turns out your answer was wrong, I give you a 0, you can't reattempt it then, right? This is, once I grade it, that's it, right? But for today, that means you can attempt participation day 5 as many times as you like today, right? Also, I realized some students might have joined the class late, or maybe they didn't have access to Canvas while we were doing some of the lectures for last week. So for that reason, participations days 1, 2, and 3, all of those can be done late, right? And I'll accept them late and give them full credit. So if you haven't done any of those yet, or you missed them because you weren't in the class yet, or for whatever reason, that's fine. You can still go back and do them. The answer for those will be in lessons 1, 2, and 3, right? Those lecture videos. So by all means, do take advantage of that. Participation day 4 and 5, those will not be yesterday. Participation day 5, you can only do today. And homework 1 is due tonight by midnight. Also, I want to go ahead and say, I've been getting several emails, and I want to clarify about the homework. No, your homework does not have to be done specifically on paper, right? If you submit your homework and you're using like some kind of app on an iPad or something, and you're writing out your work step by step, and you submit it as a PDF, no, we're not going to be like, oh, this isn't paper, that's a 0. No, that's silly, right? The whole point here for the homework is that I want your shown work to be submitted with your answers, right? It does not have to be on paper. I was just using that as an example in case you don't have a tablet. I don't have a tablet. I was not so fancy when I was going through my bachelor's. But if you have a tablet, that's great. By all means, use it, right? That's fine. The whole point here for the homework is that I want your handwritten work, whether that's electronic or on paper, I don't care, right? The whole point here is that it has to be then submitted on Canvas. It has to be submitted electronically, right? So if it's already an electronic document on a tablet, that's fine. Save it as a PDF. I don't care. So long as it's readable, so long as all your work is shown, your steps are shown for each problem, that's fine. I really don't care whether you use paper or not. That was just an example I was using for those who may not have tablets. Okay, that's all for today. That is all for lesson 5. If you have other questions, please email me, let me know. Oh, also, office hours do begin tonight at 6 p.m. There's a Zoom link on Canvas, I believe. Let me make sure. Yeah, there's a link for an office hour that will begin at 6 p.m. this evening. So office hours will be 6 p.m. to 7 p.m. on Tuesdays and Thursdays. Yeah, I realize that's kind of online class. A lot of you might be on internships, you might be traveling, so on and so forth. The day hours, you may not be available to really talk to me. Maybe you do have questions. Maybe you do need to talk to me. In that case, yeah, I'm going to be available 6 p.m. to 7 p.m. via that Zoom link. If you have other questions or, you're looking for extra tutoring help, you can email me. Maybe we can set up a separate time. Or you can also make use of the Math Learning Center, right? If you look in the syllabus, I left a link there for the Math Learning Center. The Math Learning Center also offers online tutoring. That's free. You don't have to sign up beforehand. You can just drop in, and somebody will be there who should be able to answer any questions you have. Okay, that's all for today. I will see you tomorrow. Best of luck. Let me know if you have questions.